In this video, we describe how one can define a logarithm function called the principal logarithm function for non-zero complex numbers. Let w and z be complex numbers such that e raised to the power w equals z. Because w is the exponent in this equation, we say that w is a logarithm of z. And since the exponential function is never equal to zero, logarithms exist only for non-zero complex numbers. We say a logarithm and not the logarithm because every non-zero complex number has multiple logarithms, unlike the real valued logarithm function for positive real numbers. Every positive real number has exactly one real valued natural logarithm. In contrast, every non-zero complex number has infinitely many complex valued natural logarithms. Before we elaborate on this, we introduce notation for the logarithm of z with irrational number e as base, or plainly the natural logarithm of z. This logarithm is also often written as ln(z), but in this lecture we will denote the natural logarithm of z as log(z). Let r be equal to the absolute value of z, and let theta be an argument of z. If z equals x plus I times y and x and y are real numbers, then r equals the square root of x squared plus y squared, and tangent of the argument of z equals y over x. Then z equals r times e raised to the power I times any argument of z. R equals e with exponent log r. Therefore, z equals e with exponent log r plus I times any argument of z, and a logarithm of z is log r plus I times any argument of z. Now, if n is any integer, e raised to the power 2n pi times I equals 1, so that multiplying z by e raised to the power 2n pi times I, we still get z. So z equals e with exponent log r plus I times any argument of z plus 2n pi times I, and log r plus I times any argument of z plus 2n pi times I is also a logarithm of z, so that z has infinitely many logarithms. Conversely, let a plus ib be any logarithm of z where a and b are real numbers. We will show that a plus ib equals log r plus I times any argument of z plus 2n pi times I for some integer n. Because a plus ib is a logarithm of z, z equals e raised to the power a plus ib. Dividing z by itself, and e raised to the power a plus ib by e raised to the power log r plus I arg z, we get 1 equals e raised to the power a minus log r plus I times the quantity b minus arg z. B minus arg z being the imaginary part of the exponent must be an argument of 1. All the arguments of 1 are multiples of 2 pi, so that b minus arg z must be equal to 2k pi, where k is some integer, and b equals arg z plus 2k pi. This part must be equal to the absolute value of 1, and so should equal 1. The only real number exponent for e that produces 1 is 0, so that a must be equal to log r. We rename k as n, so that every logarithm of z is of the form log r plus I times the quantity arg z minus 2n pi. Let arg z with uppercase A be the principal argument of z. The principal argument of z is the argument of z that is greater than minus pi and less than or equal to pi. Corresponding to this, we define the principal logarithm of z as the real valued natural logarithm of r, or log r, plus I times the principal argument of z. Since every non-zero complex number has exactly one principal argument, each non-zero complex number has, therefore, exactly one principal logarithm. So now we have a logarithm function for non-zero complex numbers. We denote the principal logarithm of z as log z with uppercase L. We now talk about the derivative of the principal logarithm function. The principal argument function is not differentiable for 0 and for negative real numbers. A reason being that the limit of the principal argument function does not exist at 0 and at negative real numbers. Consequently, the principal logarithm function is not differentiable at 0 and at negative real numbers, and so we assume that z is neither 0 nor a negative real number. Before we try to find the derivative of the principal logarithm function, we must first show that the derivative of the principal logarithm function exists. It would make little or no sense to look for the derivative if it were to turn out that it did not exist. We prove the existence of the derivative in two steps. First, we showed that the principal logarithm function satisfies the Cauchy-Riemann equations. And second, we showed that the partial derivatives u sub x, u sub y, v sub x, and v sub y are all continuous within the domain of the principal logarithm function. We had provided a proof of the well-known fact in the video, the Cauchy-Riemann equations and a sufficiency condition, that these two conditions together suffice to guarantee the existence of the derivative of a function. We are providing the link of this video in the description of this lecture. Let the principal logarithm function be equal to u of xy plus I times v of xy, where u and v are real valued functions. U must be equal to log r, or to log the square root of x squared plus y squared. And v must be equal to the principal argument of z. One can verify as an exercise that u sub x equals x over the sum of the squares x squared and y squared, and that u sub y equals y over the same denominator. We will find v sub x and v sub y, or the derivatives of the principal argument of z, in a roundabout way. Tangent of the principal argument of z is y over x. Differentiating this equation with respect to x, we get for the left side secant squared of the principal argument of z times the partial derivative of the principal argument with respect to x. For the right side, the derivative of y over x with respect to x is minus y over x squared. Secant squared is 1 plus tangent squared. Tangent is y over x, so secant squared equals 1 plus y squared over x squared. From this equation, v sub x, or the derivative of the principal argument function with respect to x, equals minus y over the quantity x squared plus y squared. Now, differentiating this equation this time with respect to y, we get exactly the same left side, except we differentiate the principal argument of z with respect to y. For the right side, the derivative of y over x with respect to y is 1 over x. And from this equation, v sub y, or the derivative of the principal argument function with respect to y, equals x over the quantity x squared plus y squared. We see that u sub x equals v sub y, and that u sub y equals minus v sub x, so that the principal logarithm function satisfies the Cauchy-Riemann equations. In addition, the only time each of these partial derivatives is discontinuous is when x squared plus y squared equals 0, precisely when z equals 0. We are excluding 0 from the domain of the principal logarithm function, so that these partial derivatives are continuous within the domain of the principal logarithm function. Therefore, with these two conditions satisfied, the derivative of the principal logarithm function exists for every complex number that is neither 0 nor a negative real number. So now we can proceed to find a formula for the derivative of the principal logarithm function. We will do it in two ways. For the first method, we apply the fact that the derivative is equal to u sub x plus I times v sub x, which is a formula related to the Cauchy-Riemann equations. From these formulas for u sub x and v sub x, the derivative of the principal logarithm function should equal this quantity. One can verify as an exercise that this is equal to 1 over x plus iy, or 1 over z, so that the derivative of the principal logarithm function is 1 over z. For the second method, we use the difference quotient. We choose the radial line through z along which we find the derivative. This radial line has as equation theta equals the principal argument of z. Let z plus delta z be a point on this radial line. Without loss of generality, we assume that z is between the origin and z plus delta z on this radial line. Let delta r be the distance between z and z plus delta z, so that the absolute value of z plus delta z equals r plus delta r. Then z plus delta z equals its absolute value, which is r plus delta r times e raised to the power I times the principal argument of z plus delta z. The principal argument of z plus delta z is also the principal argument of z, so that z plus delta z equals r plus delta r times e raised to the power I times the principal argument of z. So the principal logarithm of z plus delta z equals log of the quantity r plus delta r plus I times the principal argument of z. From this, we subtract the principal logarithm of z, which is log r plus I times the principal argument of z. I times the principal argument of z cancels out. In the denominator, delta z is not the distance between z and z plus delta z, but the vector from z to z plus delta z. Delta z's principal argument is also the principal argument of z. Therefore, delta z equals its absolute value times e raised to the power I times the principal argument of z. The absolute value of delta z, or the length of delta z, is delta r. So delta z equals delta r times e raised to the power I times the principal argument of z, which is now the denominator of the difference quotient. We gather everything involving r and delta r in one fraction, and all the others in another fraction. This fraction is the difference quotient for the derivative of the natural logarithm function at r. With r being positive, this difference quotient should tend to the derivative of the natural logarithm evaluated at r. That derivative is 1 over r. R times e raised to the power I times the principal argument of z equals z. Therefore, the derivative of the principal logarithm function evaluated at z is 1 over z.